Hey, hello, Philip here. This video is called Butterfly CFD Toy Plane Part 3, and I will show you several ways on how we can visualize now our data in Rhino to get a bit more out of it. By the way, before we jump in, check out my channel. There's a new button. You can join my channel as a member. You get these incredible cool gecko loyalty badges which change over time the longer you're a member, and yeah, please check it out. Okay, without further ado, let's jump into the toy plane CFD analysis visualization options. Okay, I will not go through everything again. If you haven't watched the previous two videos in the playlist, then please go back. Otherwise, you will have no clue what I'm talking about. It's complex and it needs to be done step by step. Just for the people who already watched it, just a very quick recap. We introduced the model, we created a butterfly model, then we introduced the wind tunnel and also the butterfly block mesh. And from there, we refined our model with the Snappy Hex Mesh tool. And from there, we then we talked about refinement levels and so on. And then we created the butterfly solution, the actual core tool which does the calculation. Or let's say this is like communicating with Blue Core CFD, the open form engine in the background, and we had to introduce a recipe, and we're like adding here turbulence models. There are default values in here, but just to show you. And then we introduced control points. The solution parameters with probe points. Probes you can see here. These is actually vectors, the output, but the probe points are a way to locate the specific points we want to actually measure. And to do so, we introduced a plane. On that plane, we populated points in a 2D manner. We also looked at how we can exclude points which are inside the model with the mesh inclusion option. And remember that if you use BREPs, then there's another tool, is the BREP inside option or something like that. Point in BREP, that's how it's called. So depending on what kind of model you have, you need to choose the right tool. And then we make sure that we're not testing the models inside, but outside the model. Further, then we went further to create to specify the field we're testing. We will check here because we will also measure the pressure, and we will show the pressure here as well. And then we introduced it back to the solution into the probes, and then we were retrieving the probes values by also specifying again what kind of field we're testing, U in that case, the wind speed in meter per second. We kind of scaled the amplitude or the length of the vector with a multiplication, just to make sure that these vectors are not as long as their value. We introduced a factor, which you still can change, of course. You can see that originally that's how it would look like. It's not very useful. So we using a way to scale that output. And then we just displayed our vectors. That's where we came last time. And today I want to give you some more options on how we can visualize this. One is, it's actually basically the same what we do here, but we will introduce colors. So we will introduce a gradient, a color gradient with 2 or 3 colors, and they will color the vectors according to their speed. And it's very simple, and we'll just start with that right away. So for that, we can use very simple the gradient tool in the regular gradient tool in Grasshopper. This is basically already the color. We could put here the color. Now everything is gone because there are no inputs here. First input we need to give is the values. Oh, sorry, the length. Now we already get a color here. That's very interesting. But we need to specify the maximum and minimum of these. And one way would be to just look it up. Oh no, maybe one way would be to sort the list, so we know what is the minimum and maximum. Sort list here. That gives us some clue from what is the lowest and what is the highest. Here the problem is that I have a value here which is much bigger than all the other numbers. It's probably a missed, or like it's wrongly calculated. It's probably a point which is inside the object, and that's why. So we didn't catch all the outside or inside points, and that's why it seems like an issue. But it shows us that 23 must be the maximum here, around 23, and then around 1 would be the lowest speed. So I will, in that case, of course there are now ways to deal with that automatically, and I showed that in another video at some point, but we can also just do it manually. I mean, there's no harm in doing it like this. So we can provide a number, and I would just use 0 as a minimum, and then I have another slider. I can use 100. Now it's better we introduce a different color, because it's very hard to see what is now the maximum minimum. I would choose here, maybe if you right click here, then you can choose a different color scheme. I would probably use this. This has just 3 colors, and here we can already see there's quite some difference. I go back here to 0.005. That was easier to look at, and maybe introduce the different colors. They're not very nice to look at. Yeah, so this is one way to color your vectors. Now, what I want to do is I want to show you how we can add another field to show you how that also works if we have, instead of populating points here, which we create grid of points. That will help us to actually visualize something on a mesh. And the best way is just to show you what I mean. So I want to show, in that case, we show the velocity or the wind speed around the plane, but what about the pressure, the air pressure? And we can do that by introducing P. Now it would start to calculate again. That's fine. Let's just let it calculate. Here we show the vectors, and let's get another one of these to show the pressure. We can actually just go here and type P, and now from our solution we're retrieving the vectors, and here we're retrieving the Pascal. If I look in here, I already see the numbers. Now it's a bit, it was not very useful to have this like populated points here. It makes it slightly difficult. So what I would do, I will not populate it like this, but I will create a grid. And the best way to do it is actually through Ladybug. Ladybug has this tool here, Ladybug Generate Point Grid. That's the perfect tool for this. We can actually use this here. We can use the grid size. Actually, you can already see it. And what it also does, it actually gives also a mesh. That's perfect. So we could make it smaller, of course. Let's just also stop this here. It creates a mesh and it creates the points. So that's really, really perfect. Can make this smaller. And we do the same as we did before. We add these here. So the list of points goes here and here, because we also again want to measure the inside and outside points. If I go now on a different, maybe ghosted. I didn't really change it. Change the preview, and if show this now, yes, now it works. So now we have only the points outside. So that's step 1. Now we could rerun our script. It gives a very interesting look. This is because of the size of the block mesh. The block mesh minimum smallest unit or smallest cell size is 0.3, and that's what see. That's why I kind of like the randomness a bit better, but it's still a very valid output. And we have 0.3 here, as you can see, and you almost can see the cells here. That's where they're all almost the same. And we might want to again work with, that stopped, and we can work with this, with the size. It's still too big. Nevertheless, we have now a field with the pressure values, and if we want to show that not in a vector version but as a heat map, then we could introduce the Ladybug heat map component, which is this one. Place the mesh, the values here, and because this tool also creates a mesh, then we can just introduce that here, and now it doesn't work. So if we want to if we want to create this heat map, then we also need to make sure that we have the same amount of points and the same amount of mesh faces. It's kind of crucial that this, So how to do it? So we introduce these grid points. I think that's a good start. But now the problem is if we use the mesh from here and we introduce the mesh, we're gonna add the mesh here, then we will have a different amount of mesh faces than we have points in the solution. That's the big issue. Because at the moment, if we look here, if we hide the plane, we see that we have everywhere points, and our mesh will have we'll have faces everywhere here. Our mesh, if we look at the mesh like this, then of course this mesh has the same amount of mesh faces as points in our point grid. As you can remember, we did this cull pattern where we filtered out whatever all the points which are inside the toy plane model, and we need to do something similar with the mesh. Luckily, there is a tool for that. I actually didn't know myself, but we can use cull faces tool that works with the mesh, so we can amazingly plug in here the mesh and then use the same pattern to exclude the faces we don't want to use in the mesh. How awesome is that? And in that case, we exclude stuff, so we don't need to invert the Boolean. We don't need to invert with the Boolean tool, with the invert Boolean tool. We just add this from here, and it's already working and removes all the faces inside, which are inside the geometry. Here we have 2610 points. They go in here into the cull pattern, and we end up with 1583 points, and the meshes should have the same amount, should be the same amount of mesh faces. And you can actually see here faces are 1583. They need to be always the same amount, and now this we can put in here, and when we now rerun, then we should get a heat map around the plane where we see the Pascal or the pressure, the air pressure around the plane. Recreate, I will, just in case, I will say here, toy plane case 11, and it's rerunning now. And now we can rerun. So at the moment we don't have anything here, but we can rerun the mesh, or rerun the heat map, or let's say the solution. And we should see right away the heat map. Yes! Now this is updating as we speak. Of course, we could also introduce the values in the individual individual cells. That's also possible. We could, for example, say text tag, where we provide the location, which is our points. Actually, we'll have the relay here. It's much. Let's group this. So these are my points. I can also rename that. Location of the points, and I can choose the text, and that gives me the air pressure around the plane for each of the cells. That's just one way to do it. We can also, of course, turn it off. And we can change the legend parameters here. We can set the minimum and maximum. Again, we could sort the list by what is the highest, the lowest, and provide a minimum and maximum. And we could also change the colors, provide an index here. Different indexes give you different color ranges, and we could just choose the one which probably fits the best. Multicolored, let's try the last one, 25. Nah, it's not nice. Not nice. That was finished. You can of course always also add the vectors on top. Therefore we might want to check a different color scheme here. Also interesting that you would think that the pressure is the highest where the wind speed is the fastest. It's not the case. It's actually here is the highest. So last but not least, I want to show a third way on coloring a mesh with the pressure, but directly on the model. Let's see if we can do it. That would be really cool. It's gonna be tricky, but we'll try. So in order to do that, so that would be a bit more elaborate, and we need to do two different calculations. One calculation is for this, and the other one will be a separate one. We can just copy this here. I do a separate calculation. I disconnect the probes here. I'll also turn this off just for now. It might not even work like that. Maybe I need to do it just even completely separate. But how could we do that? Okay, so first here we created a point grid, and at the same time we created a mesh, and then the mesh we filter out the faces which were inside the model. Now what if we use the mesh, the plane as a mesh, well, we still need to get the points in order to do the actual calculation. So how could we do that? We could so the first thing I do is I'm gonna create the relay. It's just so nice. The relays are so nice. Now this is my mesh. What I want to evaluate this one. Probably this is the correct thing to do. Deconstruct mesh. Let's maybe try this first. Yeah, that actually works nice. So we can use, we should be able to use just this. So let's copy the whole thing here. So this was the grid with the heat map. And now we can, since we copied this whole calculation solution, we go just from here, from the case. Maybe let's have a relay as well. Yeah, put the case here. And now for our point, for probe points, we get our mesh model and we evaluate the face normals. That gives us the center point for each face. Actually, this we don't need. We don't need to deconstruct it. Get the center point for each face of the mesh, and that we should be able to reintroduce to the probes. So we need to create probes first. We can use these points. The fields, this time we just use just need to calculate P, put this in here, we add the probes here, let's turn this off for now, and here we need to first of all add the solution and the mesh is this one here. Let's kill this, we don't need that. And now it should actually work. If everything goes right, it should work. If not, I'm not sure, then I don't know. Okay, I will recreate this here. So start a completely new case. It looks promising, but I'm scared. Yeah, I was not sure if it actually works, but it does. Just one thing. Now it looks really crazy. This whole thing. And the reason is that Butterfly skips probes, and not 100% sure why it skips certain probes in this calculation, probably because of the complexity of the mesh. As you can see, everything which is convex, so everything which is concave, sorry, not convex, concave, it seems like it was skipped. It was skipped, and then it gives you an error saying there is not enough values fitting to the mesh faces. And here these are the skipped probes. Let's hide this. So I guess if it's more simple, if it's a more simple model, then you can see a bit more. But funny thing is, it introduces this at the end back to the values. So all the values here, which are yellow, it seems like there is no, it's just value 0 or like a skipped value or something. But if your model is less complicated, it should be really cool to do that. And I'm still getting something out of it. You know, I can see that, of course, all the faces which, or let's say all the sides of the plane which faces in the wind direction have here, of course, here completely red because of the higher pressure. This is logic, but it's just also cool to see. And of course we can introduce different color schemes again. That looks quite interesting. If anybody knows on how to work with these skip probes, or if there's a way to introduce or like kind of force these to be part of the solution or the calculation, then let us know. Alright, so next time, it was a quite interesting video, lots of interesting things I realized myself, but next time we look into the OpenFOAM file in ParaView, and you will see there's way more to the whole thing than you thought there is. It's gonna be very, very interesting. Yeah, hope you see you then, and until then, hope you have a good time.